Hi everyone. So today I'll be talking about how thinking of representing data as tensors and doing tensor factorization techniques can help us tackle big data and learn latent variable models over large amounts of data, as well as being able to have theoretical guarantees for doing so. As we've seen in many talks here today, there is the challenge of data deluge in almost every domain. Right? So we have lots of data, that's images, videos, genetic data, social network data. So we have large amounts of data being collected every day. Right? And the amount is just growing enormously. But as we have more data, doesn't mean that there is more information. Right? As like this Calvin and Hobbes cartoon, for instance. So as you can see, Calvin is saying, okay, I can fill out a reader survey, I can enter all kinds of information, right? So even though I have large amounts of data, the data I have has all kinds of corruptions, there are outlier problems, there can be missing data. So with more data actually comes more challenges. Right? So in some sense, even though I have more data, I also have more variables or unknowns as I collect more data. So that's what I term it as a data desert. So why this big data problem is challenging is not only because I have large amounts of data, the information is very much hidden within this large amounts of data. Right? So the question is, are there principled approaches for tackling this big data? So we can think of this useful information as some structured, low-dimensional objects within this huge amounts of data. Right? So how do we find these low-dimensional objects is a problem that's both challenging, both computationally as well as how do I use all this data. Right? So it's literally one of finding a needle in a haystack. Right? I have this huge amounts of data. The information that I'm interested in is a small needle hidden within that. So this is where the computational challenges arises because there can be exponential number of possible low-dimensional structures within this high-dimensional data. So how do I find this efficiently? How do I incorporate these constraints that I'm aware of to find this low-dimensional structure is what makes the problem challenging. So the one way we've proceeded is to think of these low-dimensional structures as some hidden variables. Right? So I can have a probabilistic formulation of what kind of hidden effects are present in my data. And this induce low-dimensional structures in my data. And this is what I would like to discover once I've observed it. And so we want to think of these information structures as encoding relationships between these hidden variables and my observed data. Right? So now how do I go about making this into a model? Right? So we can think of a very basic approach where these hidden variables could be just these hidden groups or clusters that just kind of, in a simple picture, you can think of data points here are closer to one another than the data points that are different colors. Right? So that's the basic clustering approach. The hidden variable is just different groups of or different kinds of clusters I have within my data. Right? A more sophisticated model would incorporate more complicated relationships between hidden and observed variables. Right? So, and the question is, how can I learn these models given the data? Right? So the challenging thing is these are all unsupervised problems because I'm not assuming any labeled information that tells me, oh, this should be points all in the same cluster versus the points. So I have to discover this from data. Right? So this unsupervised problem involves finding these hidden structures from unlabeled data. So what are the methods to do this on a large scale? What are the methods where I can have guarantees that I can correctly find this hidden information are some of the problems we've been looking So first I'll give a sense of different applications where these unsupervised learning of latent variables models arise, and then I'll show how these tensor methods have a significant impact. So as I said, the very basic problem is clustering, like grouping these data points into these various groups, right? Topic modeling, as Mark talked just a few minutes ago, is to find hidden topics in documents. So again, here the latent variable are these topics, and the observed variables are the words. So we can also use the same principle to mine communities in social networks. So you can think that there are different hidden groups of people based on their beliefs or interests, and what we observe is only the social ties. So can we discover these hidden groups? Right, so even like for recommending products to users, you can first think of a probabilistic model of what are the different hidden groups of users and products, and then use that to efficiently recommend to users. Right? And all the feature learning that has been a very exciting development in machine learning over the past few years involves finding useful features of data to do classification tasks. Right? So one way to view this as like our, as mining this, you can view this as through a latent variable framework and then use the discovered features to do better classification. And we can now think of like, in various other domains such as computational biology, there are a lot of hidden factors I'd like to discover from data. Right? And there's no supervision, we don't have any label information. And where the methods that we've been working on come along is to look at moments or aggregate statistics of data and represent them through tensors. And we'll see that they have useful information to learn these hidden variable models. So for instance, if I look at a matrix, right, that can encode correlations. So that can encode pairwise relationships between the variables. For instance, in the topic model I'm sitting, I can ask what is the probability of co-occurrence of a pair of words in a document. Right? So the intuition is if you see apple and orange in the same document, the document is likely to be about fruits. Right? So this co-occurrence gives me information about these hidden variables. But it turns out that just having pairwise co-occurrence is not always enough to learn the underlying latent variable model. And that's where the tensors come in. If you have just co-occurrence of 3 words in the document, so it's a third order tensor, what we've shown is for topic models, especially these latent Dirichlet allocation, which is a very popular topic model, we can provably recover the underlying model parameters. Right? I mean, the traditional way to learn these models have been expectation maximization or these variational formulations based on likelihood function. But what these methods are doing are instead to look at these aggregate statistics or these moments. And we're representing them through tensors. And what we show is finding eigenvectors of this tensor will give us useful information about these hidden features. And we have theoretical analysis that shows that these can correctly learn the underlying model. So that's the strength of this method compared to these traditional expectation maximization kind of methods, is that we can get to the correct parameters, whereas they can get stuck in local options. And this formulation is not only true for topic models, even in the case of learning hidden communities and social networks, we can think of the tensor that encodes common friendships among different groups of nodes. And decomposing that tensor, again, turns out will give the underlying hidden communities. So I'm mostly out of time. I won't go into the details, but just to give some intuitions, when we ran the tensor method on ELK dataset, which says how different people reviewed these businesses, just by looking at who reviewed which business, we could correctly recover what were common groups of businesses. Right? And we could also discover multiple attributes for every business. It could be a restaurant, it could be a bar, and so on. So these are multiple communities for every node. And we could do this in a very fast and scalable fashion. So I won't go into the details. I recently gave a set of talks at the Machine Learning Summer School that has videos and extensive slides. So if you're interested, that would be the best resource to go into the details. And that's my group of students.